Let's take a look at this over here. Now we got a whole change of game. Everything we've looked at so far is a d versus t, but now we have a velocity versus time. I think that's probably, every time you see a plot, circle those two things to draw your attention on not only the shape of the plot, which everybody focuses, but the y and x axis. So let's do that right away. Let's circle those two things to make it stand out. Now this is a different game here because now the slope is still useful to interpreting this, but now the slope does not equal delta d over delta t, but delta v over delta t, which of course we physicists called acceleration. So now, what could I say about this plot? Well, every 2 seconds, I love to draw these little motion triangles, and maybe you should too. That'd be good for you. This is delta v. This is delta t. The delta v is, right here, 15 meters per second positive. It's an increase of 50 meters per second every 2 seconds. And it really holds that pattern even here. I don't have numbers, but it's very clear to me that this change of 2 seconds will give you the same change because the slope doesn't change. What could we, without messing with the numbers, what could we say? Well, the slope equals the acceleration. You know what? The object that made this plot had, since the slope is constant and positive, we could say the acceleration of this body was constant and positive right off the bat without using numbers. If you want to start using numbers, it gains 15 meters per second every 2 seconds. So it's meters per second every 7.5 meters per second squared positive equals the acceleration. So I want you to be able to do that, not only work with the numbers, but work with the slope, because sometimes you'll be given a plot without numbers and they'll say, imagine you were given this without numbers, just that there was velocity and time. Could you tell me what kind of motion produced this plot? You would say the slope is delta v over delta t, which is defined as acceleration. The slope is constant and positive. The object that produced this plot was moving with constant positive acceleration, so it would be 0. Then they went to 15 meters per second, and then they went to 30 meters per second, and then 45 meters per second, each second gaining 15 meters. But no, that's wrong. That's every 2 seconds. This represents every 2 seconds. So every 2 seconds, 2 seconds, 2 seconds, it gains 15 meters per second for every 2 seconds, and that's 7.5 meters per second squared. All right, the three cars are moving. Let's talk about each car one by one. What we've learned is the slope of this plot. Now circle is like I said, let's make a habit. Circling these two things, the slope is delta V over delta T, which is of course A. So what I can say about this one, since the slope is 0, I could say A equals 0, but it is actually moving though, because it has a non-zero um, velocity, so it's constant V. B, that's a constant positive acceleration, and the other, all of them are, right? Constant positive acceleration, constant positive acceleration. Now let's rank them from the highest. Let's see if rank the accelerations from largest. So the largest acceleration is D, the next largest is C, then B, then the one with no acceleration at all was A. Why? Why was D the largest acceleration? Slope equals A, and the slope was the largest. Okay, explain D. D. Now, what happened in D? It started at 10 meters per second. While everybody was moving for the first 10 seconds, take a look at D. From 0 to 10 seconds, D was not moving. It had no velocity at all, recorded velocity. And then after 10 seconds, it had the greatest acceleration because it had the greatest slope. Okay, and I think, let's see, one more page. This one again, let's do what I said I wanted you to do. Let's circle this. Now we have velocity and time. let's, without looking at the number, what do we have here? We have that, we remember that that slope equals delta v over delta t. So which is a. So look at, it's a straight line. So a is constant, constant slope, constant negative slope, or yeah, constant negative slope. It started out, let's see, 10, 15. What does each box equal? It's 1, 2, 3. Looks like each box equals 5. This is 50, isn't it? Yeah, this must be 50. Started at 50 meters per second. It got slower and slower and slower. So the other thing, we could say that the acceleration is constant negative, but we can also comment on the velocity. The velocity keeps going down the whole time. The velocity is positive, the acceleration is negative. That's called slowing down, isn't it? Slowing down. Velocity is positive. What do you mean velocity is positive? Yeah, it's positive the whole time. Okay, and the acceleration is negative. It's slowing down. Okay, and that's all we can say about that one. Now let's be careful. Let's look at this one here. Let's circle what's on here, D and T. Now what do we? Let's go back. What do we remember about D and T? The slope is delta D over delta T, which is velocity. So now we can analyze this. This is a nice, it starts out really steep. First of all, the velocity is positive the whole time, isn't it? It's got that positive tilt and decreasing in a very smooth way. Do you notice how smoothly this is decreasing? It's like an exponential plot. It's nice and smooth. So velocity is positive and decreasing. What does that mean? Positive, okay. So the velocity starts out really fast and really, really slow. It's almost zero. Oops. Super slow. Right over here. Super slow. It looks almost like it becomes zero. So the velocity is, let's cancel that. The velocity is positive and decreasing, so it's getting it's getting slower and slower. Now, how is it getting slower and slower? In a real smooth way. I wonder if you remember before, when you get slower in a real smooth way, what's also true, ready? The velocity is positive and decreasing because it's decreasing so smoothly. That shape, the acceleration is, ready? Constant negative because it's smooth. It's a constant negative. Now, the velocity is positive, the acceleration is negative. This, of course, is slowing down. It's a lot to process, isn't it? Okay, let's get this in here. Now, this is again, oops, let's get it here, get this in the picture. Displacement. Now we're going, I'm intentionally jumping back and forth. What happened here? This is quite simple. So slope equals delta what? Delta D now over delta T, which is velocity. The slope is zero, then the velocity is zero. The person started 3 meters from the start. Let's write this down. Began 3 meters from whatever you call the start. And never moved. Okay, let's rank the velocities here. Well, how do you do that? Well, velocity, let's circle delta D by definition over delta T. So rank them. This is the number one velocity. A is number one. B and C are number two. They have the same slope, the same velocity. Now, this one started off with a head start, but once he started running, he ran as fast as, actually, yeah, he started with a head start. He ran as fast as this other guy. They both, this person was just given a head start. They started X meters. This one, everybody started here, started at the starting point, and this guy also got a head start. So at the beginning, at time equals zero, these two were at the starting point. These two were not. This person, this person just never moved, did they? They would just stood there. So B and C, then a D, right? A, B, C, D. Okay. D, this person was X meters, right? This V equals 0. And there you go. 1, 2, and 3. Three velocities. This person began with a head start and never moved. Never moved. And that is it.